Welcome back, guys. Today we are diving into limits involving infinity. What happens to a function as x gets really big or really small? Does it settle down, shoot off to infinity, or approach a specific value? Stick around as we break it all down with simple examples and clear explanations. Let's tackle infinity one step at a time. So before we do that, let's notice this. Some basic facts. Whenever you have limit as x approaches plus or minus infinity of a constant, this is always equal to the constant. And when you have limit as s approaches plus or minus infinity of 1 over x, this is equal to 0. So an example is if you have limit as s approaches infinity of 9, this is always equal to the constant 9. If you take limit as s approaches negative infinity of that same value 9, you still get that constant 9. So let's use this idea to calculate the limit as x approaches infinity of 5 plus 1 over x. Remember, using the properties of limits, we know that we can distribute the limits. So we can have limit as s approaches infinity of the first term plus limit as s approaches infinity of the second term. Notice, this over here is a constant. So if we take the limit as s approaches infinity, we get our constant. This right here is the property that we wrote over here. So this also goes to 0. So our answer in this case is 5. Let's look at the second one. When you have limits as s approaches minus infinity of pi root 3 over s squared. Now using the same idea, we can have limit as s approaches negative infinity of pi root of 3, then multiplying limit as s approaches negative infinity of 1 over x, multiplying limit as s approaches negative infinity of 1 over x. Note that pi root 3 is a constant, so if we take the limit, we still have that constant. This goes to 0, this goes to 0. So we have times 0 times 0, and this is 0. One thing that you have to notice, in fact, if you take the limit as x approaches plus or minus infinity of 1 over x to the exponent of n, this will always be equal to 0 for any n greater than 0. So when we had limit as s was approaching negative infinity of 1 over x squared, instead of breaking it down into limit as s approaches negative infinity of 1 over x times limit as s approaches infinity of 1 over x, we can just say that this is equal to 0. There is no need to go ahead and say this is 0 times this is 0. You understand? You can just go ahead if this n over here is positive. Okay. Now let's look at limit at infinity of rational expressions. We are to find the limit as s approaches infinity of 5s squared plus 8x minus 3 out of 3s squared plus 2. One thing that you have to notice, whenever you have limits at infinity of a rational expression, you have to divide the numerator and the denominator by the highest power of x in the denominator. Now, looking at this denominator, the highest power of x is this, right? We have s squared. So basically, what you have to do is to divide the numerator and denominator by s squared. So you have 5s squared over s squared plus 8x over s squared minus 3 over s squared. Then you do the same thing in the denominator. So that goes to say, if, for instance, instead of s squared over here, we had s cubed, we would have divided each term by s cubed. I hope this is clear enough. So this simplifies to limit as s approaches infinity. In this case, clearly s squared cancels s squared. So we have just 5 remaining. And if we do the same thing for the second term, we get to have 8 out of x. For the third term, we have this. The same thing happens over here. This, let me use a color that you clearly see. This cancels that. So you just have 3 plus 2 out of s squared. So using the idea, we get to say 8 over x goes to 0. This is also 0, right? Using the fact that I just wrote right here. So we have 5 plus 0 minus 0 out of 3 plus 0. Note that 2 over s squared is also 0. This is because if you take the limit as s approaches infinity of 2 over s squared, you can rewrite this as, remember the property, we can take the constant outside, right? Then we have 1 over s squared. This whole thing goes to 0, right? So if you multiply it by 2, it's still 0. So we just have 5 out of 3. So my question to you is, instead of positive infinity, what if we had negative infinity? Will our answer change in that case? No. Remember, if the limit was going to negative infinity, we would have gone through the same process, so we still end up getting the same answer. I hope this is clear enough. Okay, let's look at another question. Let's look at horizontal asymptote. A line y equal to b is a horizontal asymptote of the graph of a function y equal to f of x if either limit as x approaches infinity of f of x is equal to b, or limit as s approaches minus infinity of f of x is equal to b. Now let's explain this. So in this case, right, whenever you are finding the horizontal asymptote of any function, all that you have to do is to take the limit as s approaches infinity, or the limit as s approaches negative infinity. So in this case, with this example A, the horizontal asymptote is y is equal to 5 out of 3. If you take the negative infinity, you still get the same thing, right? So we just say that the horizontal asymptote is 5 out of 3. So let's use that idea to solve this question. Find the horizontal asymptote of the graph of f of x is equal to s cubed minus 2 out of the absolute of s cubed plus 1. So in this case, let's first of all find the limit as s approaches plus infinity. Note that with this, when the main idea is the absolute of x, when x approaches positive infinity, absolute of x goes to x. So in that case, we have just s cubed over here plus 1. And using the idea that we know already, we have to look at the highest power in the denominator. So in this case, that is s cubed. And we have to divide each term by s cubed. So if we do that, we have s cubed over s cubed minus 2 over s cubed out of s cubed over s cubed plus 1 over s cubed. So we get to see that all these terms go to 0, right? So what is left is just this over this will give you 1, and this out of this is also 1, which is equal to 1. Now let's find the limit as x approaches negative infinity. So the reason we are even finding the limit as it approaches negative infinity is because of this absolute of x, because it changes it, right? It changes everything. So we have s approaches negative infinity, s cubed minus 2. Now when x approaches negative infinity of absolute of x, that goes to minus x, right? So we have minus s cubed plus 1. So that's just the differences between it approaching this and this. So this is the same as writing limit. Note that the highest power is still s cubed, right? So you have to divide each term by s cubed. So this and this goes to 0. So we just have 1 out of minus 1, which is equal to minus 1. So the horizontal asymptotes are y equal to minus 1 and y equal to positive 1. I hope this is clear. Okay, let's solve another question. We are to find limit as s approaches infinity of x minus the square root of s squared plus 16. So with this question, first of all, let's try to put in infinity. If we put in infinity, we have infinity minus infinity squared plus 16. So we have infinity minus, note that infinity squared is still infinity. And if we add 16 to infinity, it's still infinity, right? And the square root of infinity is still infinity, so we have infinity minus infinity. Note that this is not equal to 0. Infinity is a very huge number, so if you subtract a very huge number from a very huge number, it's indeterminate, right? You don't know the answer that it gets, so this is an indeterminate form. So now how do we solve this? Basically, what you have to do, remember from our previous video, whenever you have a radical, you find a conjugate. In this case, you have to find a conjugate. You find a conjugate by just interchanging the sign. So we have positive now, s squared plus 16, s squared plus 16. And remember, now since the radical is in the numerator, we just have to multiply the numerators. So we have to use the FOIL method. So first term times first term, so that gives s squared. Now this times this and this times this will cancel out. So we just have the last two terms. So we have minus, the square roots will cancel out each other. So we just have what is inside the square root, then x plus s squared plus 16. So this is limit as x approaches infinity. So if we distribute the negative in the numerator, we have this s squared plus 16 right here. So now this simplifies to minus 16 out of the square root out of x plus the square root of s squared plus 16. Note, if we put in infinity, right, if we evaluate at infinity, we get to see that the denominator is a very huge number, which is infinity. And any constant, note, any constant over infinity is equal to 0. So in this case, this is equal to 0. So the limit as s approaches infinity of this is just 0. I hope this is clear. Let's look at another example. We have to find the limit as s approaches infinity of x minus 3 out of 4s squared plus 25. So this simplifies to, note, you see, whenever you have a rational expression, you always look at the denominator, right? The highest power of the denominator. In this case, the simplest way to solve this is, over here, looking at this, what is the highest power? X, right? So just factorize x out, then you have 1 minus 3 out of x. Do the same thing in the denominator. The highest is over here is s squared. So factorize s squared out, then you have 4 plus 25 out of s squared. So this simplifies to x 1 minus 3 over x. Then in the denominator, we can break this into 2 by writing this. Now note that limit as s approaches infinity of the square root of s squared, this is equal to x. So we have limit as s approaches infinity of x 1 minus 3 over x. The denominator now is x times the square root of 4 plus 25 over x squared. So now these two terms will cancel out. So we have a limit as s approaches infinity of 1 minus 3 over x, then the square root of 4 plus 25 over s squared. Note that the limit as s approaches infinity of 1 to the exponent of xn is equal to 0. So basically, this term goes to 0, that term also goes to 0. So we have limit as s approaches infinity of 1 over the square root of 4, and this is just 1 out of 2. So this is your answer. I hope that is also clear. Now we've gotten to know horizontal asymptotes. Let's move on to oblique asymptotes. Now, if the degree of the numerator of a rational function is 1 greater than the degree of the denominator the graph has an oblique or slant asymptote. So that basically means that, for instance, if you have s cubed plus 5s squared, and this is x plus 1. If you have this, there is no oblique asymptote. Why? Because the degree of the rational function, right, of the numerator, now this is 2. Sorry, this is 3, right? Over here, the degree is 3. The degree over here is 1. 3 minus 1 is 2. So it means that there is no oblique asymptote. The difference should be 1. So if you have s squared plus 4 over x minus 3, 2 minus 1 is 1. So there is an oblique asymptote. I hope this is clear. So let's look at a question. We have to find the oblique asymptote of the graph of f of x to be equal to s squared minus 3 out of 2x minus 4. So whenever you have this, what you have to do is to do your long division. So to find oblique asymptote, you do your long division. So you have s squared. Now there's no x term right here. So we have 0x, then minus 3. So now what do we have to multiply by 2x to get the first term right here? Note that if we have 2x and we multiply it by x over 2, this just simplifies to s squared. So we can have x over 2 here. Now we just have to multiply this by this, and we have s squared here. We multiply this by this, and we have negative 2x. We always subtract, right? So s squared minus s squared, that goes to 0. Now 0 minus minus 2, that is positive 2x. Then we bring down negative 3. So now 2x goes into 2x. We have 1, so we can have 1 over here. Then we multiply. So we have 2x and minus 4. We are always subtracting. So 2x minus 2x, that goes to 0. Negative 3, so we have negative 3 minus minus 4. And that is positive 1. And we have positive 1 over here. So we can write our f of x, which is s squared minus 3 out of 2x minus 4, to be equal to, over here, what we had over here, x out of 2 plus 1, then plus our remainder. So the remainder is 1 out of 2x minus 4. So we have f of x to be equal to x over 2 plus 1, then plus 1 over 2x minus 4. So whenever you are finding an oblique asymptote, you are always going to get, this is what we call our linear term, and this is what we call the remainder. So now we have to take the limit as s approaches plus or minus infinity of the remainder. If you do so, remember, you always look at the highest power in the denominator and divide the numerator and the denominator by it, right? So we have 1 over x, 2x over x minus 4 over x. If we take the limit as s approaches plus or minus infinity, we have the numerator is 0, the denominator 2x over x, that is 2, and this is 0. So we just have 0 over 2, which is 0. So it means that this term right here goes to 0. So if that goes to 0, then we have our f of x to be x over 2 plus 1 plus 0, right? So our oblique asymptote is y equal to x over 2 plus 1. I hope this is clear enough. So first of all, you have to do your division to identify your linear term and your remainder. Afterwards, then you take your limit as s approaches plus or minus infinity of your remainder and you add it to your function. I hope this is okay. Okay, let's solve another example. So we have f of x to be equal to s cubed plus 2s squared minus 5 out of s squared plus 1. So notice that over here the difference is 1. 3 minus 2 is 1, so an oblique asymptote exists. So first of all, we do our division and we write our terms. So we have 2s squared. There is no x term, so we have to introduce 0, then minus our constants. So what do we have to multiply by s squared to get s cubed? That is x. Then we multiply, right? So we have s cubed, x times 1. Over here, there is an x. There is no s squared term, so we do our subtraction. S cubed minus s cubed, that goes to 0. 2 minus 0, so we have positive 2s squared. Now 0 minus x, so we have minus x here. Then our constants minus 5. So now what do we have to multiply by s squared to get 2s squared? That is 2. So we have plus 2 here, then 2s squared. There is no x term, then plus 2. We are subtracting. So this also goes to 0, then minus x minus 0, we just have minus x. Minus 5 minus 2, this is minus 7. So we can have our f of x to be equal to, which is s cubed plus 2s squared minus 5 out of s squared plus 1. This is just x plus 2 plus minus x minus 7 out of s squared plus 1. So this is our linear term and this is our remainder. So the next thing to do is to find the limit as it approaches infinity of the remainder. So limit as x approaches plus or minus infinity of minus x minus 7 out of s squared plus 1. So always look at the denominator. In this case, we have s squared, so it means we have to divide each term by s squared. So this is just limit as s approaches plus or minus infinity. The first term goes to minus 1 over x minus 7 over s squared. This is 1, then this is 1 over x squared. So using the property, this goes to 0, 0, and 0. So all that we have left is 0 in the numerator and 0 in the denominator, which is 0. So since this goes to 0, we just have the linear term left. So our oblique asymptote is y equal to x plus 2. I hope this is clear enough. Thank you so much for sticking by. If you have any question, just let me know. As always, I would appreciate it so much if you give this video a thumbs up. I'll see you in the next video. Bye.